Ladies and gentlemen, welcome to this technical presentation by the Royal Institution of Naval Architects and the Institute of Marine Engineering, Science and Technology. Our presenter this evening is Sally Garrett. She's the research lead at the Defence Technology Agency in the New Zealand Defence Force. Sally was educated at Takapuna Grammar School in Auckland, New Zealand, and then obtained her Master of Science degree in Environmental Science at the University of Auckland in 2000, and subsequently a postgraduate diploma in meteorology from the Mississippi State University in 2009. She began her career in 2000 as a graduate with the Defence Technology Agency in the New Zealand Defence Force, moving on to become a research scientist, then environmental lead in environmental science, and in 2016, research lead for the Defence Technology Agency. She's focused on increasing the safety and efficiency of sailors, soldiers, and aircrew. Key areas of research include the development of a safety software tool for amphibious operations, development of an environmental requirements for future Royal New Zealand Navy ships operating in the Southern Ocean and Ross Sea, and characterisation of the Southern Ocean and Ross Sea waves. She supported the New Zealand sailing team at the 2008 Olympic Games by collaboratively developing a tidal model for the sailing venue in Qingdao. Sally's also a yachtswoman of note and was Commodore of the Royal Akarana Yacht Club in 2016-17, race director for ANZ's Sail Fiji in 2016, and is now a member of World Sailing's Subcommittee on Special Regulations. She is also the reigning New Zealand Women's National Keelboat Champion and was the leading female helm at the last Flying 15 World Championships. Ladies and gentlemen, I'll pass you over to Sally Garrett.
Well, thank you, everybody, for giving me this opportunity to come along and talk to you a little bit about the work that we've been doing in the New Zealand Defence Force since about 2009, characterising the wave climate of the Southern Ocean and Ross Sea. Usually when I talk about this topic, I usually only have a very short amount of time to talk, but today I suppose I've got a little bit longer. And so what I'd really like to do is I'm going to start off by showing you a video of the why. Many people ask me, why is the Royal New Zealand Navy and the New Zealand Defence Force so interested in Southern Ocean waves? And why have they decided to lead a program of wave observation and wave study in the area? So I've just got a video to play first. Oh, no. Okay.
So Operation Castle is the Navy's contribution to the overall operations south of New Zealand. That's headed by the Ministry of Foreign Affairs and Trade, and so our part within that is to bring the Ministry of Primary Industries as the experts in all things fish to come with us and be those subject matter experts. So the Navy in this case is a delivery asset as an enabler, at the same time trying to deter all the unlicensed fishing vessels, which thankfully we've been able to do for at least the last 2 years. So Targo left New Zealand middle of November. We routed down towards Dunedin, and from there we've operated south over the whole Christmas, New Year holiday period. Over that time, we've been launching boarding parties, inspecting vessels, checking their catch, checking their documentation. But really, that's only part of it. The biggest part is ensuring that all the conservation measures are met. So that includes everything from waste management to good maritime pollution prevention measures, making sure that they're actually looking after this part of the world, because it's all about not only the fish, it's about the entire package. It's protecting this continent and all of its resources. Part of the design of the offshore patrol vessel was to bring into account the fact that we can operate from the equator right down here to the pole. The Navy hasn't really operated in these sorts of extremes for the last 40 years. It's only been the last 2 or 3 years that we've really started to get back down here again. And that brings a number of challenges, and it's not just the ship design, but that's also the way we operate. So it's something new and it's something very challenging. These ships are designed to be able to push ice around, but in moderate conditions. They're not icebreakers, they're ice strengthened. This season we've learned a lot, really finding out where the capabilities of this ship is. Obviously we've got a lot more cold weather gear available to us now, and you're probably going to see that a whole bunch of our guys and girls have got all sorts of different colour gear on as we trial new pieces of equipment and make sure we're getting the right piece of kit. But that's just one of the many lessons that we're learning as we go through, and one thing the Navy prides itself on is being able to learn a lesson very quickly and adapt to change. So the offshore patrol vessel is obviously well suited to this kind of role. We've got space, we've got a lot of capability, we've got 2 jet boats on board, room for a helicopter or other air assets, but also wider New Zealand Defence Force. There are Army here, there are Air Force here, we've got the P3 Orion on call should we need it. So it's not just a Navy deal, this is a whole of New Zealand approach to our responsibilities on the Antarctic continent. Although the Antarctic is nobody's, and at the same time it's everybody's. So while it's not anybody's patch, it's on our beat, if you like. The fact that we're sending an 85-metre offshore patrol vessel with 60-odd people on it, 2,000 miles south of New Zealand into the Ross Sea, that's a big thing for a country like New Zealand to be doing. So I think that really speaks volumes for how important we think this part of the world is.
So that video really kind of outlines what the New Zealand Defence Force is up to, or the Royal New Zealand Navy is up to in the Ross Sea. We're routinely completing fisheries boarding inspections in the Ross Sea. So today my talk is going to follow a pretty straightforward sort of pattern. I'm going to talk a little bit about our motivation, talk about the current knowledge of waves in the Southern Ocean, our wave observation program that we've been running since 2017, our wave modelling optimisation that we did for the Southern Ocean, the hindcast that we completed, and then some results about the new wave tables or scatter bivariate wave height, wave period tables, wave spectra and spectral spreading techniques that we've been looking at. And then finally, a little bit about the work that we're hoping to complete next season. So what's really interesting about the Ross Sea and the Southern Ocean is that the challenges that ships' crews face today are exactly the same as those that were faced by the explorers of the heroic age. The Southern Ocean is known for extreme waves, and the Ross Sea sea ice is highly variable in thickness and moves around a lot. The New Zealand Government's Defence Capability Plan, released in June 2019, sets out the plan for investments for the New Zealand Defence Force to 2030. Included in this plan is the purchase of an ice-strengthened ocean patrol vessel for Southern Ocean and Ross Sea operations. To design and build such an ocean patrol vessel that is not only safe and but also able to effectively complete required operations, a deep understanding of Southern Ocean and Ross Sea waves is required. Since 2011, the Navy has routinely operated south of 60. At each deployment, the ship's command team have reported extreme sea states that have been poorly forecast. These videos are taken from an Otago-class offshore patrol vessel operating in the Ross Sea. The camera that they were taken from is about 18 metres above sea level. The ships were operating in areas of open water surrounded by sea ice. These types of areas in the Northern Hemisphere are often associated with very, very low sea states. But in the Southern Ocean, in the Southern Hemisphere, ships operating in the Ross Sea are exposed to large waves from the Southern Ocean moving south into the areas of sea ice. We know from our own measurements in the summer months that the average wave height in the Ross Sea in the presence of sea ice is sea state 5, 2.5 to 4 metres, with periods of time with wave heights greater than 10 metres or sea state 8 in the presence of ice. The sea ice of the Ross Sea is highly mobile, variable in thickness, and has denser inclusion. These sea ice properties, coupled with very high sea state, differ greatly from the conditions of the Northern Hemisphere and will require any ice-strengthened ship that is designed to operate in this area to have a very good understanding of the conditions. So what do we know about the Southern Ocean? While the Southern Ocean makes up 22% of the planet, very little is known about the waves of the area. The industry standard database for wave heights for design is the Global Wave Statistics that many of you will have come across that were published by BMT in 1986. This database is based on observations from ships and is regarded by many as the best source of data for design. The map on the slide shows the Global Wave Statistics sea areas. The red boxes are where we would like to operate. Shown in the blue is the North Atlantic areas that were used by the International Association of Class Societies to form their North Atlantic scatter table. This is widely used for ship motion modelling to define the worst case conditions. From the observations of waves by our people at sea, the condition they are experiencing in the Southern Ocean and Ross Sea are extreme. Due to a lack of data in the area, it is unknown if the North Atlantic scatter table adequately describes these conditions. Understanding the difference, though, between the Southern Ocean and the North Atlantic is not a new area of work. Stuart Cannon from DSTG Group and his co-authors presented their comparison of wave loading effects on Anzac frigates operating in the Southern Ocean and North Atlantic in 2004. The study compared the modelled bow slamming for North Atlantic areas shown in blue with the Southern Ocean, Indian Ocean areas shown in red. Southern Indian Ocean areas were used as no true Southern Ocean data was available. Cannon modelled the slamming pressure and the total numbers of slams for head seas only for all sea areas. On this slide, in both plots, the x-axis is the ratio of significant wave height to ship length. On the left plot, the y-axis is the number of slams, and on the right, it is the pressure of the slams. Sea Area 100 in the Southern Indian Ocean had the greatest number of slams. Across all areas, the number of slams in the Southern Ocean was 1.5 to 3 times greater than that of the North Atlantic. The greatest slam pressure was also in the Southern Indian Ocean. The pressure on average of across all sea areas was 1.2 times greater in the Southern Indian Ocean than the North Atlantic. The results of the studies, however, was considered very conservative, as there was no winter data available for the Southern Indian Ocean. The study provided a great first look at the differences between the Southern Ocean and the North Atlantic, but was really limited by the lack of data available for the Southern Ocean in winter. The New Zealand Defence Force shipbuilding program requires a characterisation of wave conditions year-round in the Southern Ocean to 78 degrees south. Our initial studies of waves in the area focused on ship observations from voluntary observing ships. Ship observations in the Ross Sea and Southern Ocean are currently limited. This map shows the average number of observations per month for the period of 1950 to 1997. The light shading of the Southern Ocean indicates less than 5 observations per month on average were recorded. However, the map doesn't show the variation between summer and winter months. Studies by Italian researchers en route from New Zealand to Terra Nova Bay in the Ross Sea highlighted the very low number of observations in the Southern Ocean in winter. Only 88 observations south of 60 existed between April and September for a 40-year period ending in 2000. These very low numbers of observations have been associated with a high sampling bias. In the Southern Ocean, studies have shown that the wave height can be underestimated by ship observations by as much as 1.5 metres because of fair weather bias. Ship-based observations were therefore deemed unsuitable as a sole source of data for developing a shipbuilding wave climatology. Satellite observations in open water do provide a year-round, unbiased method of characterizing wave height. However, altimeters, the most common sensor used, cannot be used to estimate wave height in the presence of sea ice or in other non-Gaussian surfaces within the sensor footprint. To enable a year-round understanding of wave climates in all areas of the Southern Ocean to 78 South, a three-part approach was used. In situ measurements of waves were completed using wave buoys. The data from these buoys was used, along with satellite altimeter measurements, was used to validate a Southern Ocean and Ross Sea optimized setup of the WaveWatch 3 model. And then this model setup was used to create a 24-year hindcast of the area. To fill the gap in observations of waves in the Southern Ocean, the Defence Technology Met Ocean Solutions, which is part of our New Zealand Met Service, and the Royal New Zealand Navy deployed the first directional wave buoy into the Southern Ocean, south of 42 South, 11 nautical miles south of Campbell Island on the 27th of February 2017. The buoy on the left, on the crane, is the directional wave buoy. The first buoy deployed in 2017 broke free in July and roamed the Southern Ocean for over 2 years before it finally ran out of battery. A second board buoy was deployed in 2018, which survived until May 2019, and then was replaced, unfortunately, in November 2019 by a buoy that only lasted 3 months on station and broke free in a period when the average wave height for 10 days was greater than 10 meters. In addition to the moored wave buoys, we've put 23 free floating wave buoys into the Southern Ocean, as shown on the right of this slide. And they have been deployed between 42 South, which is the South Island of New Zealand, and 67 South, which is the northern part of the Ross Sea. This New Zealand Defence Force-led project is the largest wave observing project to be implemented to date in the Southern Ocean. So we've just got a couple of, a map and a graph of what we've been up to. So on the left is a map showing New Zealand and the Ross Sea to the south. So our wave buoy observations are focused on the area to the south of New Zealand where our ships operate. The map on the left shows the tracks of each of the buoys that were deployed, the colours indicating the type of wave buoys that were used. The blue tracks are from the Scripps Institution of Oceanography buoys that measure wave height using GPS. The advantage of these buoys is they last a very long time because they're low battery consumption, but they're unable to provide us a maximum wave height. The green track is the moored buoy from 2017 that broke free. And the red ones are the new spotter wave buoys, which is a US initiative, which is putting over 200 wave buoys into the Southern Ocean next summer. On the right-hand side is a time series with latitude on the y-axis between 70 South and 40 South at the top, with time between January 2017 and July 2019. This time series plot shows that most of the measurements that we have all occurred in summer, when of course our ships are in the Southern Ocean. So we've measured some really big waves. In the past 3 years, we've measured, the largest wave was 23.8 meters. And to give that some context, that's the same size as a 7-story building, and only 2 meters less than the biggest wave ever measured globally, which happened during a hurricane in the Atlantic. The hourly average significant wave height during this period, when we measured the 23.8 meter wave, was measured to be 15.8 meters. Only the moored wave buoys are able to measure maximum individual wave height for a given hour. The 2 histograms show the distribution of the individual wave heights measured. For the buoy deployed in 2017, it provided 200 days of data before it broke free, with a median maximum wave height of 5.5 meters, with the 2018 data buoy providing similar results. It is expected that even larger waves will be measured when we can get a buoy back on station. But modelling suggests that when we measured the 23.8 metre wave at Campbell Island, it was approximately 200 miles from the largest waves in that May 2018 storm. So having an array or a series of buoys across the Southern Ocean has enabled us to look at how average significant wave height varies as you head south. So on this plot, we've got latitude on the x-axis and significant wave height on the y-axis. The maximum hourly significant wave height for all deployed buoys was greater than 9 meters. 10% of the buoys recorded periods of time when the hourly significant wave height was greater than 14 meters. And you can see that the average wave height across the Southern Ocean from 45 to 70 south was sea state 5, except for one buoy that got caught in the sea ice. So how does this compare to the North Atlantic? In these plots, the North Atlantic data, the International Association of Class Societies North Atlantic Scatter Table, is shown in red. The conditions measured at Campbell Island are shown in black, and the conditions in the Ross Sea are shown in blue. The left plot shows that the peak significant wave height distribution measured at both buoys is greater in the Southern Ocean and Ross Sea than we see in the North Atlantic Scatter Table. The right plot shows that the wave periods of the Southern Ocean and Ross Sea observations are greater than those within the North Atlantic Scatter Table. Our first priority with this research has been to improve the safety of our sailors at sea by improving our ability to forecast extreme waves. Wave forecast models for all ocean basins have a specific setup. These have been developed by validation against wave conditions that have been observed. For the Southern Ocean, the global wave model, WaveWatch 3, is usually set up using the defaults for the North Atlantic, with no optimisation ever occurring due to limited number of observations. Clearly, from the experience of our people, this way of setting up our wave model is not providing very good forecasts. To improve Southern Ocean wave forecasts, the United States Office of Naval Research provided the New Zealand Defence Force and Met Service a 3-year grant to enable the WaveWatch 3 setup to be optimised for the Southern Ocean. The biggest improvements from the default setup of the model was due to changing the way that wave energy dissipates and by adding ocean currents to the model. On average, the new setup was between 5 and 20% closer to the altimeter and buoy observations than the old setup. In this map, red is where there has been an improvement in our ability to model observed wave heights, and blue is where the accuracy has decreased. And this work is available in a published paper in Ocean Dynamics. So once we were happy with our setup, the next thing we decided to do was to create a hindcast. So this is running a forecast model in the past. And so we completed a hindcast at a resolution of 0.25 of a degree by 0.2 degree from 31 south all the way around the world for a 24-year period from January 1993 to December 2017. We used the European Centre for Medium Range Weather Forecasts reanalysis as our wind field and the GLORIS reanalysis of currents. And we calibrated against the limited amount of altimeter data that was available in the northern part of the Ross Sea. So this data is all available. And what it looks like is for every one of those 0.25 by 0.2 degree points, there is a wave period, wave heights bivariate table. And this is available to the public, to anybody who wants to use it. But to design a ship, we really need to understand the wave conditions for a period of 20 years or more. 20 years or more. And so this hindcast provided the only way to really do it. So when we think back to the global wave statistics and the way it divided up the ocean, the area covered by the 104 sea areas were quite small blocks. And in most cases, the location and shape of these blocks covered areas where wave characteristics varied considerably. And it's thought that those blocks were actually created by where National Weather Services had jurisdiction. For example, Area 104 covers both the eastern and western approaches to Cape Horn, areas with a dramatically different wave climate. The intent for our newly developed wave atlas was to divide the hindcasting models into a series of sea areas with similar wave characteristics. To do this, we completed the mean significant wave height, the standard deviation of the wave height, the mean period, and was taken for each point for 300 months, and was then clustered using a k-means algorithm to find areas of similar wave characteristics. So this map shows that clustering. Now, I thought this was great, but the naval architects weren't so happy with this as an idea, because it's very difficult to work out which cluster you're in. So we took that and we went to a more conventional scheme where the irregular borders of the initial clustering were transposed onto a 5 by 5 degree grid to form a sea area map, as shown here. So how do the characteristics of these new sea areas compare to those currently used by ship designs? As previously mentioned, the International Association of Class Society North Atlantic Scatter Table, or bivariate wave height wave period table, is used within ship design to describe the worst sea conditions a ship is likely to see. On this plot, with significant wave height on the x-axis and occurrence on the y-axis, the North Atlantic data is shown in red, and each of the sea areas in the Southern Ocean Wave Atlas are shown in grey. 12 of the Southern Ocean sea areas, including those to the south of New Zealand, have a peak significant wave height greater than that of the North Atlantic. Moreover, 8 zones have a higher proportion of waves greater than 6 metres than the North Atlantic, and 2 zones have a greater proportion of waves greater than 8 metres. For 18 of the 20 sea areas in the Wave Atlas, including the one to the south of New Zealand, the peak of the peak period distribution is greater in the North Atlantic than it is, greater than the North Atlantic, with all sea areas having a greater percentage of waves with a period greater than 12 seconds. The New Zealand Defence Force has presented these scatter tables from this to the class societies over the last month or so, and is trying to get information on the implications of this more energetic wave climate on design rules. A desired outcome is the development of a Southern Ocean notation for design. So the current status of this project is that there is a report available on request. I think you can find it on our website, but if you can't, please email the librarian and she'll send it out. This report has gone out to the class societies, and Lloyd's have now recommended that this data be included if you're designing a military ship for operating anywhere in the globe. The International Association of Class Societies are looking at the wider implications of this more energetic wave climate. And the New Zealand Defence Force has committed to using this for all seakeeping modelling for future and current ships, including our new project, which is to develop and design a light icebreaker, the Southern Ocean patrol vessel. But understanding the wave height, wave period table is just the start to understanding the waves of the Southern Ocean. And for those of you who complete seakeeping, you'll know that you also need to understand the shape of the wave spectra. So at what frequencies the energy is present, and also how spread, directionally spread that energy is. So on the left here, we've got two wave spectra. The black one is a measured data from Campbell Island, and the red is using the wave characteristics of wave height and wave period. This is what John Swap would model for that area, and you can see they don't really line up. The other thing is spectral spreading, which is how the energy is spread around the mean wave direction. And there's very little known about spectral spreading in the Southern Ocean. My colleague Kevin Ewens wrote a paper about this, where he created a model that used latitude and gave you an estimate of spectral spreading. But the furthest south location he used in this was the wave buoy at the Maui platform at 42 South. So both he and I were concerned that we maybe were underestimating spectral spreading in our wave models. So once we'd completed the wave atlas, we went on to start looking at spectral optimization. So we looked at spectral models that were used in seakeeping code or ship motion code, for instance, Pearson, Moskovic, John Swap, and she's got a spelling mistake, and Thorsten Haven. And we took some observations, the observations that we'd collected, the directional observations that we'd collected at Campbell Island, just over 6,678 of them. We were able to get from the Antarctic, the Australian Antarctic Division, some omnidirectional data, 2,800 spectra from there. And we looked at two different types of fit. We looked at least squares fit, which provided us with a sensitivity around how well a model did in at modeling the spectra in the vicinity of the spectral peak, and equivalence of equivalent spectra, which gives you an understanding of the whole shape. We then looked at ranking which model out of the three that we were looking at did, who was the winner, which model was the winner, but also which ones were the second and third and fourth. And this is kind of what it looks like. We had many graphs like this. The top graph is all of the data from Macquarie Island. We split the data by sea state between sea state 3 and 9. The bottom is for Campbell Island. And we went through for each spectra. We worked out what the wave height and wave period was for that spectra. We then modeled with 5 different models. So we had the core models and then some variations on the peak enhancement factor and tail slope. And then the model that won would get 5 points, and the model came second got 4, and so on. And that's what these graphs were. And we worked through this process for quite some time, and then looked using equivalent spectra to find out which instances, which spectra a specific model underperformed in. So this was, I think it was about 1.5 years of looking at lots and lots of spectra. But we came up with an optimized spectra, which is the Thorsten Haven model with a peak enhancement of 1.9 for the primary component, a secondary component of 1, and a fetch of 1,000 kilometres. So this has been accepted by Navy, and as I said, has gone to the International Association of Class Societies. The details in the model are available from the original paper from 2004, and also the optimization details are available in a report that can be is available on request from our librarian at DTA. The final thing that we had to understand, and this has probably caused me the most headache because it happened over our level 4 lockdown, the Navy suddenly needed to decide this, which is the spectral spreading, which is how much we're looking at linear waves and when how much spread spectrum we want to have. So the Navy has always used the NATO standard, which is a cosine squared function and gives us a spreading angle of about 32 degrees. If we look at the two plots that we have, this is the data from Campbell Island. On the left, we have the mean wave direction. Effectively, the waves come from the west to southwest. And on the left, on the right, we have the RMS spreading. So this is how spread is the data that we're observing at Campbell Island. So when we look at these spectra, the average spreading angle is around 40 degrees, which is considerably or significantly greater than what we would get from the NATO standard. We have some concerns about the buoy data. First of all, we just don't believe we have enough to change from the standard. We're also concerned because we don't get the raw data off the wave buoy because it would be too power hungry to send that much data. And unfortunately, and this is my boss gets onto me about this, I've actually lost 3 wave buoys in the Southern Ocean, so I've never been able to download one. So we do have some concerns that the spectral spreading is actually greater than 40 degrees, and that we may have periods of time where we have 2 very different wave trains affecting the buoy. And so this is future work. So at the moment, we're continuing to use the NATO standard from 1983. So that's kind of the completion of the stuff, the work that we've been doing in the open water of the Southern Ocean. But the new work, or the work that we started around the same time, and we found much more difficult to resolve, is really about waves in ice-infested waters. So that picture that I showed before of, an icebreaker rolling around in the Ross Sea. So just going back to this video, because you think, oh, but there's something actually more menacing in this video, just in water breaking over the bridge of a ship. There's actually really big pieces of sea ice. So this is just a still from this video, and you can see circled in red, there's very large pieces of ice. We've had reports of pieces of ice the size of minivans suddenly arriving next to the ship. And you can see visually how difficult that is to see because you think it's white water. It's impossible to see these pieces of ice using a radar. And these pose significant risk to a ship. As you probably are all aware, minimally ice-strengthened ships just have a thick or a double layer of steel and ice strengthening an ice belt around their waterline. And if this piece of ice that's floating around in these waves doesn't hit that, it hits the top sides. The thickness of the top sides is just like a normal ship, so 6 to 9 millimeters. So we started off looking at what this would look like. So this is an OPV. The red is the size of our ice belt. And this is just in a standard wave field. We're using ship motion. This is before we really got into spectra in the Southern Ocean. And you can see there's considerable amounts of time where the grey, the normal part of the ship, is at the waterline. And this is quite concerning, really. So we have been completing wave measurements in the Northern Ross Sea. And as I said before, there is significant amounts of time where in the presence of sea ice, we're seeing very large wave heights. And I'm just at the moment involved with VARD, with the first concept designs for the Southern Ocean Patrol vessel. And they really quizzed me on this because they do not see this in the Northern Hemisphere. So on the left is just a time series of a wave buoy that we've put into the Southern Ocean. And you can see it was deployed in about 3/10 sea ice in March, and by April it was in 10/10. But in that period when it was in between 3 and 10/10 ice, we had 3 occasions with very large sea states. So this is average wave heights greater than 8 meters. And if we look at the distribution of wave heights in terms of percentage, we can see that the waves in the Northern Ross Sea are very, very similar to the observations that we saw in the Southern Ocean at Campbell Island, and are greater or more energetic than those that are in the North Atlantic scatter table. So my colleagues, this is some work I did. We looked at, well, what do the spectra of waves within the sea ice of the Ross Sea actually look like? We clustered using some techniques from Les Hamilton, who's a DSTG researcher. We clustered the spectra for different sea states, see if there was a typical type or one spectral shape that was more common. And then we took that and we completed sea keeping. But before we get to the next slide, so the next slide is about the results of that, and just so that we all understand what we're looking at. There's these plots that are coming up. They have the ship in the middle, and as we work around the ship, it has which direction the waves are coming from. The further away from the ship we are, is the ship going faster, and closer to the ship's hull is when the ship's going slower. So we completed, my colleagues completed with my wave data, a series of ship motion studies, and they did that with a polar patrol vessel. They had two different types, and they had a light tanker and a heavy tanker with different forms of ice strengthening, so PC 1 to 4 or PC 5 to 7. And then they looked at how much of the time would the protection of the hull be at the waterline in each of these different sea states. Sorry, in each different sea state. So if you look at the top plot, when it's dark green, it means that 80% of the time the ship would be protected. And then as it goes to lighter green, there's less and less protection. And this is a paper by Andy Marsland and Ed Ballard, which was presented in Sydney in 2019. And this is the work that we're now starting to do for our actual concept designs of ships that we're operating. So in creating the operational limits for our new PC6 tanker, we're able to take the spectra and look at what wave conditions she can have adequate protection from her ice belt. When we look at new designs for the Southern Ocean patrol vessel, we can use these wave spectra to understand how big the ice belt needs to be for the performance we want. So where are we at? This is my final slide. You know, with the Southern Ocean Wave Atlas, we've published a report. You can email us and get a copy of that. The hindcast data is also all available on request through our threads database on the unclassified internet. We're completing some seakeeping modelling using ShipMo 3D, using the Southern Ocean wave spectra, and also more standard wave spectra for polar type hull shapes to see what the actual effect is in terms of ship motion. We completed a series of 5 additional buoy deployments in the Ross Sea this season, and we're looking at an extended cruise in the Ross Sea in February 22 on our tanker with 10 to 15 deployments of wave buoys. All of our wave data is available in Australia on the IMOS platform. So if you want to download it, it's all there. And that's it for today.
Okay, that's great. Well, thank you very much, Sally, for your presentation. We have a number of questions, I think. Well, I can see that we have one there from Martin Grimm, but maybe if I could ask the first question, and that is, Sally, you mentioned earlier something about the highest wave ever recorded, and you said it was in the North Atlantic. Many moons ago, when I was chasing the same sort of thing, I found that the highest wave ever recorded was 112 feet, which I think is about 34 meters, by a US merchant vessel in the mid-Pacific during a tropical cyclone. So maybe you could tell us what the latest figure is for the highest wave ever recorded.
Yeah, well, that was something because so the World Met Organization say that it's only 25 meters. And that's because it was a significant wave height. So it's the top third of waves averaged was 25 meters.
Oh, okay. So that's
Yeah,
the
rather than
significant wave height.
Yeah.
But do you have a figure for the single highest wave ever
No,
recorded?
we didn't.
No.
We didn't. Yeah. Yeah.
Oh, okay.
I think personally the thing that I've noticed that's really unusual about the Southern Ocean is because I advise command teams before they go down there, is there's many times where they get a front or a low pressure and they have 18 hours of these massive waves and they've just got to wait it out. But what we saw last year in May when our last wave buoy broke free, as I said, was 10 days when the average significant wave height did not go under 10 meters for 10 days, and it pulled our wave buoy, dragged our wave buoy, and then broke its mooring. So it's just not only that the waves are big, it's that they persist for a really long time.
Okay, well, let me just go back up here to the question box, and Martin Grimm said, not sure if we're using the chat facility. This presentation by Sally is lovely, covering so much interesting ground. Spectra with double peaks may have quite different ship motion responses than the equivalent TZ single peak spectrum. I wonder if it is time to define spectra more carefully with scatter diagrams.
I'm not sure about that, but the model that we chose, the Thorsen-Hagen, actually does have the ability to do bimodal spectra, and that's why we chose it. What we know about the Southern Ocean spectra is they have a very wide base, which is indicative of multiple storms affecting the waves at one point. So typical John Swap sort of single peaked data is associated with fewer storms affecting it. So it's like the waves from a single storm create that spectra. What we know about the Southern Ocean, where the low pressures lap the planet in 7 days, is that there's multiple storms all affecting the wave conditions at a single location. And we see a very broad spectra, even if it isn't double peaked. It's very broad. And that's what we were trying to capture. And that's what we're trying to understand with our comparison between traditional wave spectral models and the one that we've optimized to.
Oh, right. Oh, that sounds sensible. Now, we have another question here from Alastair Mitchell. He says, with this new data, has the Navy altered how they operate offshore patrol vessels, i.e. where they operate and the times of year, etc., noting the ice belt limitations?
Yes, so our Navy no longer sends the Otago class OPV to the Southern Ocean, and we're building a new ship. So yeah, pretty, as a scientist, that's a pretty big endorsement of your work, but when the ships were designed, they were designed for Baltic conditions, which are very low sea states. And now we know that that isn't the conditions that we're operating in, that they would be outside of the design limits.
Okay, somebody, Matthew Stubborn says, thank you for a very interesting presentation. Maybe if I could ask a question, did I see HMNZS Otago, was she an Anzac class vessel? I thought the Anzacs were Takaha and Tamana. Yes,
so the Otago and Wellington are what we call Otago class OPVs. They're a VARD 85 metre design offshore patrol vessel.
Oh, okay. And where did that design come from? Was that from Sweden or somewhere?
So VARD is in Canada.
Oh, okay. All right.
So they designed the Nathaniel B. Palmer, the Canadian AOPS, ships, the Harry de Wolf class, that are just coming online, have quite a heritage in polar vessels.
Right, okay. Well, ladies and gentlemen, do we have some more questions for Sally?
So, Phil, I just sent one through. Can you hear me? Yeah.
I can hear you, Martin, yes.
So, Sally, again, thank you for that presentation. It's amazing what you guys are doing, guys in the generic sense, over there in New Zealand. You know, we used to use the BMT scatter diagrams many years ago, and including when RAN ships started heading further down south. And yes, it was dead obvious that the boxes in the manual just run out as you go further down south. So yeah, it is amazing what measurements and work you've been doing over the last, I guess, many years. I'm still curious about. You've now explained that the spectrums that you're considering, or the spectra shape, has got 2 peaks in it. But does this then mean that you will in future have scatter diagrams where you've got more than just a significant wave height versus a period and the probability of all those occurring? I mean, it just becomes more and more variables. There's wave direction, there's, you know, the period of both of those peaks, etc. I'm just trying to understand how that works.
Yeah, so what's really interesting about the bimodal spectra is that we scientists thought that that's what you'd see down there. And I mean, out of that 6,000 spectra that we had in the first kind of set of wave spectra, we did see some, but it was a very low percentage. It was like less than 2%. And it also only happened at low sea states. But what we did see was this very broad spectra. So very broad-based spectra, which the way you create that in a spectral model is to use a model such as Thorson-Haven, which was really designed to be broad-based because it could have 2 spectral peaks. So it's been a huge relief, I think, to our naval architects that they aren't having to really consider at higher sea states. So, you know, average sea state of 5 and above, they don't need to worry about bimodal spectra. And even, you know, sea state 4, which is where most ships are at the limits or close to the limits of their operations, such as helicopters, we don't need to consider it because there was no spectra measured at that, like that.
Yeah, okay, thanks for that.
Yeah.
Okay, ladies and gentlemen, any more questions?
Phil, can I throw one more in?
Of course, Martin, yes.
It's this whole question of, so Sally, the videos you showed, it certainly showed sort of footage where one of those Otago class was more than likely slamming occasionally. That typically happens when the wavelength and the ship lengths are fairly similar. Whereas in some of your other slides, you were showing, if I understood it or, you know, interpreted it all correctly, that the typical wavelengths you're seeing, or the wave periods you're seeing down in the Southern Ocean, are longer than, say, the North Atlantic. But so I guess what I'm pondering over is, you know, slamming events are obviously bad for ships in terms of the structural response. Wave steepness is bad. So on the one hand, you've got sort of large wave heights, but on the other hand, you've actually got longer wave periods. And so this sort of reminds me of work that was done in our department many years ago, where, yes, whilst the wave height is larger, the wavelength is also longer. So the net effect on, say, accumulation of fatigue, at least on the face of it, is actually not as dramatic as you'd think it is. But if you then factor in, you know, again, I'm going back to the, you know, the shorter waves more cause the slamming. If your strip theory code is not properly accounting for slamming responses, then you're sort of neglecting a whole effect that's going on. So this is a convoluted question, but I guess what I'm getting at is it's really important to make sure that wave definition you've got is really properly accounting for the combination of the wave height and the wave period, and including what effect it has on slamming. So maybe it was more an observation than a question, but maybe you've got some comments on that.
Yeah, so this is, of course, the naval architects came back to me with that a while ago. And so, you know, for some of the applications, for instance, like hitting sea ice, it's not really slamming that's a problem. It's, you know, waterline height. But for our recent testing for the Southern Ocean Patrol vessel, we've used a combination of the short wave periods of the North Atlantic with the more energetic waves of the Southern Ocean. So we've actually been testing both rather than writing off the North Atlantic data, because we feel that our ships need to operate globally. So we need to be able to perform in both conditions.
Okay, thanks.
Yeah.
Okay, any more questions, ladies and gentlemen?
Phil,
Yes, who's
it's
that?
Ray. It's Ray.
Ray, how are you?
I did put one into the chat, and I guess while Martin is heavily into the maths, I'm not so heavily into the maths. So I was interested as to what approach Sally takes when she briefs the ship's crews to try and, let's say, I assume she tries to convey this in a more practical sense, you know, rather than 1,000 plots and spectra.
Yeah.
You know.
Yeah. Well,
So,
I mean, yeah. So the information I give to the ship's crews is quite different to what the naval architect gets. You know, I suppose the things that we talk about, so leading up to a deployment, I probably spend 6 to 8 weeks off and on talking with the ship's crew about the conditions down there. And I suppose the most important thing is to really reinforce to them the why. So why are you going to get big sea states? Well, you're probably going to get them when there's a change in wave direction. Under a cold front, like there's certain weather phenomena that are associated with the worst sea conditions. And some of it's about giving them confidence and saying, you know, most of the time in the summer months, you're only going to see a big sea state for 12 to 18 hours. You're not going to see it long term. In terms of spectra, though, it's more, I think for New Zealand sailors, they're very used to confused seas, and they're very used to operating in conditions where the spectra is quite broad-based, you know, waves coming from lots of different places, different periods. They don't know that's what it is, but they know what the conditions are like. And so I suppose the spreading and the spectra is not really anything I talk about. It's more the limitations on the forecasting and as I said, just trying to give them some confidence that it's not going to last too long, because I think that's what you need to know if you're 2,000 miles from safety.
okay, thanks a lot.
Yep.
Okay, thanks, Ray. I haven't seen, I'm sorry I missed your question there, Ray. It was actually above the one from Martin that he piped up about, so I totally missed yours. I'm sorry about that. If there are any more questions, ladies and gentlemen, this is just about the last time of asking. Okay, well, it just remains for me to thank Sally very much for your very interesting presentation. I think you've held us all enthralled with what's happening down there in the Southern Ocean. And I want to thank you on behalf of RINA, the IMAR EST, and all of tonight's participants.